Okay, good morning, Austin and Dorothy. So today I'm going to be talking about nuclear medicine. So, how do we utilize radioactive isotopes in medicine? So, let's start with the concept of radioactive decay. So, radioactivity or radioactive decay talks about how some isotopes are not stable, meaning they can disintegrate, and as they disintegrate, they can emit a radiation. So there are several types of radiation that they can emit. It can be alpha, it can be beta radiation, it can be gamma radiation. There's also the positron radiation. So what you need to know are the three radiations: alpha, beta, and gamma radiation. So what is alpha radiation? When this unstable nucleus emits an alpha radiation, it means it emits two protons and two neutrons. So two protons and two neutrons, which is very similar to a helium atom. A helium atom has two protons and two neutrons. So we normally use this symbol to show an alpha decay, or this one, an alpha decay. So an example is, for example, you have radium. If it undergoes alpha decay, so it loses two protons, two neutrons, so the atomic number becomes 86 and the atomic mass becomes 22. So minus 4, then minus 2. Okay. Another radiation is a beta radiation. So when a radioisotope undergoes beta decay, okay, listen carefully. A beta decay is when the neutron becomes a proton and an electron. A neutron transforms into a proton and an electron. So in this case, this boron, one neutron transforms into a proton. So you have an additional proton. So the atomic number increases. It becomes carbon 12. Okay, atomic mass stays the same because the neutron just transforms into a proton. And neutron and protons have the same mass. Okay, at the same time you emit an electron. Okay, so for alpha decay you emit a helium atom. For beta decay you emit an electron. All right, so let's look at some examples. So for example, you have astatine 211 and it undergoes alpha decay. So alpha decay, as I've mentioned, is minus 2 here in the atomic number, minus 4 here in the atomic mass, because you lose two protons and two neutrons. So as it undergoes alpha decay, it becomes, what did I just do there? Okay. Ooh. I don't know what I just did with that. Well, anyway, so minus 2, 83, atomic number 83 is bismuth. Let me just check. 83 is bismuth. Yes. Okay. So another example here. So we have yttrium 90. It undergoes beta decay. So it means the neutron transforms into a proton and it emits an electron. So minus 1 is, sorry, plus 1, neutron becomes a proton, becomes atomic number 40, zirconium. Okay, and then this is how you notate a loss of electron. All right. Now, when radioactive isotopes decay, it means over time there's less and less of that original isotope. And we have a concept called a half-life. A half-life is basically how long does it take for your radioisotope to become half of its original amount. Okay? And half-life varies from isotope to isotope. It's different among different isotopes. For example, for radium-226, the half-life is 1,600 years. But for radium-224, it's faster, 3.7 days. What does this mean? Radium-226, every 1,600 years, that's a long time, it becomes half of its original amount. Whereas in radium-224, only about 4 days. Okay, let's looking at this graph right here. So for example, we're looking at an isotope and its half-life is 2 seconds. So it means every 2 seconds, it becomes half of its original amount. So let's say the original amount is 8. So after 2 seconds, it becomes 4, half of its original amount. After 2 seconds, it becomes 2, so half of 4. After another 2 seconds, it becomes 1. Half of 2 is 1. Okay? So I think it's an easy concept. All right. So let's discuss it more. So for example, I have radium-226. It's an alpha emitter, as we've seen earlier. It has a half-life of 1,600 years. It's actually pretty stable compared to many of the other isotopes. Okay, so if we start with 1 gram, after 1,600 years, you have 0.5 grams. After another 1,600 years, you have 0.25 grams. So it's half of its original amount every 1,600 years. Okay? Alright, so let's look at an example here. So we have germanium-71. It has a half-life of 11 days. If the original amount is 2 milligrams, what is the mass after 44 days? So 2 milligrams. Half-life is 11 days, it becomes 1 milligram. Another 11 days, it becomes 0.5 milligrams. Another 11 days, it becomes 0.25 milligrams. Another 11 days, so that's the 44th day, you have half of that, 0.125 milligrams. So the mass is 0.125 milligrams after 44 days. Very easy example. Let's look at another example. So what is the half-life? This time you're being asked the half-life. Protoactinium-233. Ooh, that's a fancy element. Protoactinium. Hold on, I just want to see it in the periodic table. Protoactinium? How? On octium, we only have 100 protoactinium. Mass. Anyway, the symbol. Okay, ignore me. Oh, PR. PR is the symbol. Atomic number 59. Okay, so it takes 108 days for 100 milligrams to decay to 6.25. What is the half-life? So from 100, you now have 6.25 milligrams. What is its half-life? So, and it takes 100 days for that. Okay, 100 milligrams, half-life became 50. Another half-life became 25. Another half-life became half of that, 12.5. Another half-life became half of that, 6.25. Now, you had 4 half-lives there. And in the problem, it says it took 108 days to decay. So 108 days divided by 4 half-lives, 27 days. So a half-life is 27 days. It becomes half of its original amount every 27 days. Okay, so also easy example, right? So let's go into how do we apply or how do we make use of these radioactive isotopes in medicine. Now, so radioactive isotopes, when they decay, they emit alpha, beta, gamma, neutron, positron emissions. Okay? And when we take advantage of that, 2 ways. First, we use radioisotopes or radionuclides we use it as medical tracers. Okay? I think we've learned this in the past, so a little bit of review for you here, but more in-depth. Number 2, we can also use them to treat a disease. So number 1, for diagnosis, so you want to know where the problem is inside the body. Number 2, there's something wrong in the body and you kill it with radiation. So you diagnose or you kill it with radiation. Okay, so as medical tracers. So as medical tracers, we use radioactive isotopes and we put it in another molecule and we can inject it inside the body. And the movement of this radioactive isotopes, because it emits radiation, we can detect its movement. We can pick up where their radiation is. Okay, common radioisotopes use gamma or positron emitters. Positron is like a positive electron. Okay, classic example is technetium 99. So as you can see here in the picture, what I have here is, so this is the aorta, the biggest artery connected to your heart is here. So you have an aorta, and some people they suffer aortic aneurysm or abdominal aneurysm. It's when the blood vessel to the aorta and then the blood vessel to the stomach becomes really big and then it ruptures. So to know whether, let's say I complain of a stomach ache, or actually I feel this when I'm full, I feel like a palpitation in my stomach area. Do I have enlargement of my blood vessels there? So what they can do is they can inject a radioisotope, and then the radioisotope will go inside the body, and once it's inside the body, be quiet, it emits radiation, so gamma radiation. So we can detect that radiation using technology. And here, as we can see, this is normal. A person with abdominal or aortic aneurysm will have a distended blood vessel. So you can trace the inside of your body by putting a radioactive isotope that emits radiation. So it's inside your body and it emits radiation, then you can detect where it is. You can trace the insides of your body. Popular example is technetium 99. You actually need to know this by heart. So, what is technetium 99? Technetium 99, it's a popular choice for as a medical tracer. Hold on. It's the most common radioisotope used as a tracer. And there are three reasons why we use technetium 99. So first is its half-life. It only The half-life is 6 hours, meaning it becomes half of its original amount every 6 hours. And that makes it very ideal because the isotope that you inject to the person doesn't really stay long inside the body. So the exposure to the radiation is minimized. Okay. Second reason why we use technetium 99. Second reason is because it's metastable. That's what the letter M stands for. It's metastable. It means it can just exist for a short period of time. As I've mentioned, its half-life is only 6 hours. Then lastly and most importantly is its chemistry. So as the technetium 99 disintegrates, it emits photons very similar to X-rays. Okay, the wavelength is similar to X-rays. So when we take it in, we ingest it or we inject it, we just use an X-ray machine to follow. So these are an example of pictures of an X-ray machine to follow where it is as it emits its energy, a photon, very similar to X-ray. Okay, and the energy or the radiation emitted is very low, so it's not as dangerous even if you inject it inside the body. And it has several oxidation states. So it has several oxidation states, meaning we can combine it with different kinds of ligands. Yeah, you already know what a ligand is. So we can make several types of technetium 99 to target and to image different parts of the body. So let's go on now to the second use of your radioisotopes. So not only can we use them to trace what's inside the body, so what's going on, what's wrong inside the body, we can also use the radiation from radioisotopes to treat, to cure. So we call it radiotherapy. Therapy means to cure. We cure using radioactivity or radioisotopes, using radionucleotides. So there's two types of therapies that you need to know: internal and external radiotherapy. So for internal radiotherapy, as the name implies, internal, you put a radioactive substance inside the body. This time not to trace, but to kill, to cure. So once it's inside, it disintegrates and it kills Okay, but what do we want to kill, Miss? Why do you want to kill cells? Well, there are inside the body cancer cells. So we take it in, and then it goes inside a cancer cell, and then it kills the cancer cell. So for these internal radioisotopes, it's radioisotopes used for internal radiotherapy. We normally inject it inside the body, or we put it inject it in the blood, or we take it as oral capsules. Okay. Now, external radiotherapy, as the name implies, external. So you subject your body to ionizing radiation. So there's a radiation, and then it kills the cancer cells inside the body, or a specific area inside the body that you want to target. So let's look at internal radiotherapy. So first technique that you need to know is brachytherapy. So what is brachytherapy? This involves using a solid radioactive substance, and then you insert it into the body. For example, an area near the tumor. Okay, and this is used to treat several types of cancer, including prostate cancer, cancer of the head, neck, womb, or cervix, but most commonly for prostate cancer. So you inject the radioactive substance near the area where the tumor is, and normally we use palladium 103 or cobalt 60. So these radioactive substances emits gamma radiation. So once it's inside, it disintegrates, it releases gamma radiation, and then that radiation is good enough to kill the cells around the area or the tumor. Okay. So that's one, brachytherapy. Another procedure we can do is we take liquid that can be taken orally or through the blood, intravenous. And for example, for thyroid cancer, we can give them iodine 131. It's a pill, it's a capsule. And once you take it, it goes inside your blood, it circulates around the body, but it concentrates here in the thyroid gland. It's because the thyroid, to function properly, it uses iodine. So any iodine from the blood will go into the thyroid. Okay, and here in the thyroid gland, you will have cancerous cells. Now, this iodine is taken up by the cancerous cells also in the thyroid. And then, this iodine 131 will start to emit beta radiation. Okay, this type of radiation can kill those cancer cells. So as it disintegrates, the radiation kills the cancer cells. Okay. Now, yttrium-90 and lutetium-177. So these are radioisotopes that emits beta radiation, and they have very relatively short half-life. So it's okay to inject it inside the body. Now, as you can see here in the picture right here, yttrium-90, we attach it to other molecules, and then we make it into a tiny bead. Now, in the liver, the blood vessels supplying blood to cancer cells are very small. Okay, the blood supply to cancer cells are very small. So these tiny beads containing this yttrium-90 is able to go into this location. And once it's there, yttrium-90 will disintegrate and emit beta radiation. Okay, and therefore, as it emits beta radiation, the radiation is strong enough to kill this cancer cell. Okay? Alright. Okay. Another example is lutetium-177. As I've mentioned, it's a beta emitter. So, this in general, we can use it to treat different kinds of diseases. Normally neuroendocrine cancers, so cancers of the nervous system, so cancer of the brain or cancer of the different glands around the body that produces hormones. So to simplify, so we have lutetium-177, we attach it into an antibody that can specifically target receptors of neurons or cells of the the glands. Okay, so as it attaches to that cell, so this is the cell that we want to kill, it disintegrates. As it disintegrates, it produces beta radiation enough to kill this cell. All right, so just let's review all of those examples we've discussed so far. So this one is palladium 103 or cobalt 60. We use them in brachytherapy. Another one is iodine 131. We use it to treat and kill cancers of the thyroid. And then we have yttrium 90. We use it to kill cancer cells of the liver. And then we have lutetium 177. We use it to kill different kinds of cancer cells, normally cells that are found in your nervous system or your cells of your different glands around the body that produces hormones. Okay, so let's continue. Now, targeted alpha therapy. So this is another treatment that you need to know. For targeted alpha therapy, so you inject a radioisotope that disintegrates and releases alpha radiation. Okay, and then once it's in the target site, this disintegrates, and alpha radiation is much stronger than beta radiation. So as it disintegrates, it kills the cell where it's attached. Okay, this radioisotope to antibodies, and in bio we've learned antibodies attached to antigens. So if we have a cancer cell, it has a receptor that can serve as an antigen. Then we design an antibody that can attach to that antigen, and we attach a radioisotope to that antibody. So as it attaches to the antigen, the isotope can start to disintegrate, and alpha radiation is very strong. Can kill that cell around that area. It says here, this is useful, by the way, because antibodies are specific to the antigen that they bind to. So as soon as you study the antigen of a cancer cell, you design the antibody that can attach to that antigen. About 20 alpha particles are required to kill one cancer cell, so there's a lot of radioisotopes being used here. And antibodies will target one type of cell anywhere in the body. So TAT has a great potential to treat cancers that have spread throughout the body. So let's say your cancer cell is not just in the prostate, it has metastasized. You've learned that in bio. It has spread to other body systems. So you have the cancer cell in the prostate, but then it's also in the liver or it's also in the lungs. These cancer cells also have the same antigen. So you inject the antibody with the radioisotopes and it spreads around the body looking for that cancer cell with the antigen. Once it binds, the radioisotopes disintegrates and emits alpha radiation, killing these cancer cells. The second type of radiotherapy is external radiotherapy. So very obvious here in the picture. External radiotherapy is you have a machine that generates the radiation. So inside the machine, you have radioactive isotopes here inside the machine. As it disintegrates, that the radiation that it produces, you use it to target cells in the body. So the radiation is coming from here. Then it's emitted to specific areas of the body. And we have different machines that can produce different types of beams of radiation. We normally use this for chemotherapy. So we expose a cancer patient to a chemotherapy using beams to kill those cancer cells. And if we do that, there are obviously side effects. Okay, so hair loss. This can occur when the beam of that ionizing radiation enters and leaves the body. So if it also affects the cells of the scalp, then you get hair loss. Nausea. Nausea is, for example, the radiotherapy is around the area of your abdomen. So the radiation also affects the cells of your gastrointestinal system. So you get that feeling of you want to vomit. Okay, because even your healthy cells are affected. And fatigue, obviously, if you expose the body to ionizing radiation, then the red blood cells can also get killed. So you feel more tired because you don't have that oxygen carrying capacity from your red blood cells. Then sterility. If the treatment, the chemotherapy, targets the area of the here in the lower extremities, then it can also cause damage to your normal cells in your reproductive system. It can cause sterility. Make sure you can list down these side effects of radiotherapy. Okay. Now, the last type of nuclear medicine that you need to know is boron neutron capture therapy. Now, this one is a combination of internal and external therapy. Miss White, okay, as you can see, you inject boron 10 inside the body, so that's internal radiotherapy, right? So boron 10 will go inside the body, then you can trace where it is. And what you do is you expose that part of the body to a neutron source reactor. So this is you have a radioisotope here inside that emits neutron. Okay, and this neutron you bombard it to boron 10. Why, miss? What does it do? As you can see here in the equation, the boron 10, when exposed to neutron, becomes this unstable isotope, boron 11, which can readily disintegrate into this and emit alpha radiation. Bombarded with a neutron, it becomes this unstable isotope that can emit an alpha particle. Okay, this alpha particle is strong enough to kill cancer cells. So let's say you have cancer in the brain, so you inject boron 10. After that, you expose yourself to external radiotherapy. So we have beams of neutrons targeting that area in your head. So the boron 10 there becomes an unstable isotope boron 11 that can quickly disintegrate and produce alpha radiation, which can kill the cancer cells here in this area of the brain. So it's called boron neutron capture therapy, because you inject a boron, and then once you locate where the boron goes, you target it with a neutron gun. So you have a neutron beam. So you capture that neutron, and this makes your boron unstable, therefore emitting alpha radiation, which can kill that area of the body, kill cancer cells, kill neighboring cells around the tumor. All right. So I said boron neutron capture is your last nuclear medicine, because magnetic resonance imaging is not really nuclear medicine. We don't use radioisotopes in MRI. Okay, although it's included here in this chapter because MRI deals with a nucleus. Okay, but it doesn't deal with the radioactive nucleus. So what we're talking about here are the nucleus of your your hydrogen atoms around the body. So carbohydrates, proteins, lipids, nucleic acids, they all have hydrogen. And we have learned, in the past, that hydrogen, when you subject it to a magnetic field, it can spin. It can spin. So our body, which has a lot of hydrogen, when I put my body inside an MRI machine, the magnetic field can spin the hydrogens inside here in my body. And we can use that to detect things inside the body. So for example, this is your MRI body scanner. You go there, you go inside. Let's just say we're looking at the brain. Let me see if I still have a slide. Oh, never mind. So this is the whole body now. So your MRI, so the machine, once you switch it on, the magnetic field interacts with all of the protons, all of the hydrogens, which are in all of your organic molecules. So this can interact with all of those molecules in different parts and different organs of the body. And you can read your body, basically. So connect the MRI is connected to a computer, and you can have a scan of the body. So you can scan the different parts of the body, because different parts of the body will have structures or environment. So when you apply the magnetic field, it spins differently in different parts of the body. So you can have a scan of the body. We normally use MRI for brain scans. So if you want to see the activity of different parts of the body, the brain is cells carrying blood, obviously, to your brain. And then of the blood, of course, has water, so we can use that to image the brain. Okay. Again, it's part of nuclear medicine because we're using the hydrogen nucleus of the different organic molecules inside the body. Then we subject it to a magnetic field, and depending on the structure, we can have a of visualization or an image of an organ or different parts of the body. For example, another example is if you're gonna need a knee surgery, so they're gonna do an MRI scan first of the extent of the damage on the knee. So you can have an image or a picture of the area of the knee where the ligaments are injured, probably, so you can have a better idea of the procedure that you're gonna do for the surgery. Okie dokie. So thank you for listening. Hope you learned something.